Download. We'll use the Jamboard thing. Same thing as last lesson. Can everyone see if the link works? The link should be in the chat. Okay, we'll get started. So today the lesson is on combinatorics, which I think is like counting. Okay, sorry, I'm back. So first we have some problems for everyone to try. Just do as much as you can. Try to do them in order because I'll present them in order. Okay, hopefully everyone's had some time to do the first few. So yeah, I'll present the solutions for the first three. Okay, can everyone see the screen? So for problem 1, how many words can be created from reordering ABC? So we try to figure it out. We have ABC, ACB, BAC, BCA, CAB, and CBA. Okay, there are no other reorderings. And the way to prove that is if the first letter starts with A, then we got these two. And then the second letter can be B or C. So there's only those two possibilities. Then if the first letter starts with B, we get these two. Then the second letter can be A or C. And then if the first letter starts as C, then we got two more possibilities. And the first letter can only be A or B or C because there are no other letters. So we get 6. The other way to calculate this, which is how people normally do it, is 3 factorial, since we got 3 letters. Factorial means the integers like multiply together. So n factorial is equal to 1 times 2 times 3 times up to n. And this is because, right, for the first letter, right, if we consider a reordering of ABC, it has to be 3 letters. And then this first letter, it has 3 options, A, B, or C. And then the second letter has 2 options, right, the 2 letters that weren't selected for the first letter, and then the third letter only has 1 other option. So that's how you get 3 factorial, which is equal to 6. The next problem was how many 3-letter words can be created from the letters A, B, C, D, E. Right, that's a very similar problem. For the first letter, we have 5 options. For the second letter, we have 4 other options. Then for the third letter, we have 3 other options. So we get 60. Next problem was how many words can be made from reordering A, B, C, C. This is very similar to problem 1. So you would think the answer is 4 factorial, which is equal to 24. However, that is wrong. Because remember in problem 1, we considered if the first letter is A, and then if the second letter is B, for example. Then if the third letter is C, then the fourth letter is C, because that's the remaining letter. But then if the first letter is A, and then the second letter is B, and then the third letter can be C again, because in our solution for the first problem, we assume that each of the letters were distinct, which they were in that problem. However, in this problem, they aren't. Right, for example, if we labeled the C, if we made the C's different, let's call them C1 and C2, then we can assume if the first letter is A, then if the second letter is B, then if the third letter is C1, then C2 is forced. If the first letter is A, then B, then C2, then it's C1. Then if the second letter is C1, then B, C2, C2, B. Right, and that's all of the cases if the first letter is A. Then we got B, C1, and C2. However, C1 and C2 are not distinct, right? In this example, I labeled them to like let you know why we're double counting some cases. And the exact number of cases we're double counting is 2 times the actual number of cases, right? Because for example, if we have this case, A, B, C2, C1, then we also counted A, B, C1, C2. However, both of these are A, B, C, C. Right, again, in the third case and the fifth case, those two are the same if we remove the labels for the 2 C's. And the fourth case and the sixth case are also the same if we remove the labels. So therefore, if we had the labels to make the 2 C's distinct, then we have 4 factorial, which is 24 ways. However, every case is counted twice, so we divide by 2. to get 12. So you guys can continue doing the problems. Okay, hopefully that's enough time. So the next problem was how many words can be made from reordering A, B, C, C. So, 3 C's. Okay, so when there were two c's, we did 4 factorial over 2. Who the heck is drawing PPs on my thing? Okay, now there's 5 letters and 3 c's. Okay, great. My pen just broke. That's you guys gonna have a video of my mouse writing. So you guys think it's 5 factorial over 3, which would be 40, I think. Okay, yeah, no, it's not 5 factorial over 3. And the way to prove this isn't a proper proof, but like the intuitive understanding. Alright, if we label the c's again, then we aren't counting every case only 3 times, we're actually counting it 6 times. 6, which is 3 factorial. And that's because consider A, B, C, 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 right? We have this is A, B, C, C, C. And we also have this, and this, and this, and this, and this, right? Because the ways to arrange C1, C2, and C3 are 3 factorial, which is 6 ways. For another example, we have like, okay, A, C, C, B, C, right? Then we could have C1, C2, C3, C1, C3, C2, C2, C1, C3, C2, C3, C1, 3, 1, 2, and 3, 2, 1, right? The same thing as here. So that's why we do 5 factorial over 3 factorial. Next problem, we had A, B, C, 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 C. And, right, using what we just did, 6 factorial over 4 factorial, which is 30. Okay, and, okay, never mind, that wasn't the problem. The problem was A, B, B, C, C, C. Okay, so again, consider how many times we're double counting. We label the B's and the C's to make them distinct. And A, B, E, C, C, C. We could have 1, 2, 1, 2, 3, 1, 2, 1, 3, 2, 1, 2, 2, 1, 3, 1, 2, 2, 3, 1, 1, 2, 3, 1, 2, 1, 2, 3, 2, 1, and then 2, 1, and the same stuff. So we overcounted by 12 times if you do that. And that's because there's 2 B's, right? So we got 2 factorial ways to arrange the B's, and then 3 C's, so 3 factorial ways to arrange the C's, and that's equal to 12. So to calculate this, we got 6 factorial over 2 factorial times 3 factorial, which is equal to 50, I think. Okay, and now for the next problem. How many words can be made from reordering an n-letter string consisting of R1s and n minus R zeros? Okay, this is actually very similar to problems 4 and 5. Right, we got n factorial, and then we count the number of times we're double counting, right? There's R1s, so that's R factorial, times the n minus R zeros, n minus R factorial. By the way, if you guys have any questions, make sure to ask. Right, and again, if you want to think about it, then you label the ones and label the zeros. Right, and there's R ways to rearrange these and n minus R ways, n minus R factorial ways to rearrange these. Final question, how many different selections of 3 letters can be made from the 8 letters A, B, C, D, E, F, G, H? So we want to select 3 letters, and the order doesn't matter, right? We just select them. So we got, okay, consider this. We have 8 options for the first letter, and then we have 7 options for the second letter, and 6 options for the third letter, which is 3, 3, 6. However, this is incorrect because again, we're double counting. Because consider, right, in this example, we selected A, then D, then F, but consider if we selected D, then A, then F. Right, these two are the same 3 letters being selected. And the number of times we are double counting is the number of arrangements of this, right? So we got A, D, F, D, A, F, D, F, A, F, D, F, A, D, and F, D, A. So 6, which is 3 factorial. So it's 8 times 7 times 6 over 3 factorial, which is equal to 56. Okay, I mean, this is kind of provable. It's weird to prove. It's more just like something you should try to intuitively understand. So we'll continue with some more problems. Alright, so this was the last 2 problems. Alright, when we made selections, the number of ways to select R items from n, a total of n items, is n factorial over R factorial times n minus R factorial. And the way you notate that is big brackets and n and R. Right, if you actually calculate it, 0 choose 0 is 1, 1 choose 0 is 1, 1 choose 1 is 1, 2 choose 0 is 1, 2 choose 1 is 2, 2 choose 2 is 1. Right, so we're following the rows of the Pascal's triangle. Hopefully you guys know what Pascal's triangle is. If you don't, actually, so the Pascal triangle starts with 1 and then 2 ones, and then every number underneath it is the sum of the 2 numbers above it. That's what Pascal's triangle is. So, yeah, try to like intuitively understand why selecting R items from n items is n factorial over R factorial times n minus R factorial. I'll give you guys a minute. Oh, am I still sharing the... Oh, wait, never mind. I think it's okay. Okay, so for that formula, right, n choose R is equal to n factorial over R factorial times n minus R factorial. When we select R objects, right, like, okay, these are our selections, there's R of them. Then we got n options for the first object, n minus 1 for the second, and n minus 2, all the way up to n minus R plus 1. We times all of that together, that's equal to n factorial over R, no, n minus R factorial. right? Because n minus r factorial is equal to n minus r times n minus r minus 1 all the way down to 1. And then and then n factorial is equal to n times all the way down to 1. So the rest of n factorial, which was not included in here, is n minus r factorial. Okay, however, in the selection of R objects, there's R factorial ways to rearrange them, and we don't care about order, so we're overcounting by R factorial ways. Got to prove that. Okay, next, just to recap, I think you guys learned about induction in the first lesson. However, just in case you're not that comfortable with it, induction is a way of proving statements. So say you want to prove a statement is true for all positive integers n. So n is equal to 1, 2, 3, 4, 5, 6. Then we can prove it by proving it is true for the lowest case, which is n equals 1. And then proving if it's true when n is equal to k, then it's also true for n equals to k plus 1. Right? That second thing is like a proof. Like it's like a theorem that we're proving. Right? So then therefore, since it's true for n equals 1, by the second thing that we proved, it's also true when n equals 2. And so therefore it's also true when n equals 3. So it's true for every n. So there we got some example problems of induction. Try to do them. I'll give you guys a few more minutes to do problem 1, and then I'll do it just to give an example of how to prove something with induction. Okay, so hopefully that's enough time to solve problem 1. Yeah, so we want to prove 1 plus 2 up to n is equal to n times n plus 1 over 2. Alright, so when n is equal to 1, then the left-hand side is 1, and the right-hand side is 1 times 2 over 2, which is equal to 1, so it's true. When n is equal to 2, the left-hand side is 1 plus 2, which is 3, and the right-hand side is 2 times 3 over 2, which is also 3. And then, right, when n is equal to 3, we got this. By the way, you guys only have to go up to n is equal to 1. I'm just doing some more to show you. Okay, so if it's true, assume it's true for n equals to k, where k is some number. So assume this is true. That's when n is equal to k. Then when n is equal to k plus 1, the left-hand side is equal to 1 plus 2 plus up to k plus 1. And then using this, which we assume to be true, we know that this is equal to k times k plus 1 over 2 plus k plus 1. Alright. And that is equal to k plus 2 times k plus 1 over 2. And this is what we wanted to prove, right? Because n is equal to k plus 1. So if we substitute it, that's what we should be getting. Therefore, we've proven it's true when n is equal to 1, and then we've also proven that if it's true when n is equal to some number, then it's also true for the next number. So therefore, since we proved it's true for the lowest number, we've proved it's true for every number. Okay, so you guys can continue trying the next problems. Okay, hopefully you guys have realized that problem 2, you're not trying to prove it for when n is equal to 1, you're trying to prove for when n is equal to 4. Alright, because that first step, what you're trying to do is proving it for the lowest n. So then using the second step, you're proving it for every n. Okay, hopefully you guys have had a go at the problems. And I'll give you guys a few more minutes. Okay, hopefully that's enough time to try the problems. Question 2 was for n bigger than 3. We want to prove n factorial is bigger than 2 to the n. So when n is equal to 4, we got 4 factorial, which is equal to 24. And we want to prove that it's bigger than 2 to the 4, which is 16. So that's true. When n is equal to 5, 5 factorial, which is equal to 120, is bigger than 2 to the 5, is equal to 32, which is true. When n is equal to 6, 6 factorial, which is equal to 720, is bigger than 2 to the 6, which is equal to 64. And again, that is true. When n is equal to 7, we got 7 factorial 5040, 2 to the 7, which is 128. And something that hopefully you noticed is the difference is becoming quite big, right? This was like barely bigger. This was already quite a bit bigger. This was a lot bigger. And now it's like, yeah, very easy to tell that it's bigger. Okay, so okay, this tells us that we can probably make quite a lot of like big, big like implications, I guess, in your induction step. It's still probably true, right? Like we could divide this by 10 and it's still bigger. Okay, so assume k to the factorial is bigger than 2 to the k for some k. Then k plus 1 factorial is equal to k factorial times k plus 1, which is bigger than 2 to the k times k plus 1, right? Because we have this. And this is bigger than 2 to the k times 2, because k plus 1 is k is already bigger than 3. Actually, we know k, okay, since we've already proven it for these, we can actually assume k is bigger than or equal to 8. Actually, 7. K plus 1 is bigger than or equal to 8. But that isn't really necessary, right? We could have just proven this, and we already know k plus 1 is therefore bigger than or equal to 5. So this is definitely bigger than 2, and that's 2 to the k plus 1. So we've proven it. Right. Okay, this is a bit rude. I'm a bit insulted. I think my handwriting's pretty beautiful. Okay, so the next problem, we have 7 to the n minus 1 is divisible by 6 for all positive integers n. Again, when n is equal to 1, this is equal to 6, which is divisible by 6. When n is equal to 2, that's equal to 48, which is divisible by 6. When n is equal to 3, that is 342, which is divisible by 6. Okay, so suppose 7 to the k minus 1 is divisible by 6. Then 7 to the k plus 1 minus 7, right? So we times that by 7, is also divisible by 6. And we plus 6, right? Because the multiple of 6 plus the multiple of 6 is still a multiple of 6. And that is equal to 7 to the k plus 1 minus 1. Final question. We know 1 plus 1 over x is an integer. And we want to prove that x to the n plus 1 over x to the n is an integer. So when n equals to 1, it is quite clearly true. And that's all we need for the first step, right? And then we just prove that if it's true for n equals k, then it's also true for n equals k plus 1. But just to demonstrate, and normally when you're doing problems, right, you should keep going, right? Don't just prove n equals to 1, and then that is enough to like do your proof by induction. But normally like trying small cases does give you more insight, and that can be enough to let you figure out how to solve it. Right, so then when n equals to 2, you got x squared plus 1 over x squared. And this is quite similar to this. So we try squaring it. And squared is equal to x squared plus 2 times x times 1 over x plus 1 over x squared, right? And that's just 2. So this is equal to this minus 2, which is an integer. Because this is an integer, so this is an integer, minus 2. It's still an integer. And then we keep trying stuff. Okay. You got many options, I guess. You could try x plus 1 over x is a 3, which does work. But also consider that eventually you're going to have to do n equals to k, and then that's a bit nasty, right? So instead, we can try something else, right? Maybe 1 over x squared plus 1 over x squared times x plus 1 over x. And then we have to subtract x and 1 over x. Okay, immediately, this is an integer, this is an integer, and this is an integer. So this is an integer. Again, x to the 4 plus 1 over x to the 4. Maybe this time you want to try x squared plus 1 over x squared. But this idea seemed to work last time, so we'll try to use it again. And then we got to subtract x squared and 1 over x squared. Right, because this is equal to x to the 4 plus x squared plus 1 over x squared plus 1 over x to the 4. Again, integer, 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 so this is an integer. And then, right, assume it's true for n equals to k, right? This is an integer. Then k plus 1. We just continue our concept, our previous idea, right? We hope it just keeps working, which it does. Oh, actually, right, this isn't just induction. In our normal induction, we assumed if it's true when n equals to k, then it's true for n equals to k plus 1. But if I finish this proof, we prove this, which is equal to this, is an integer. We know this is an integer, and we assumed this is an integer. However, we also have to assume this is an integer, which we can, right? It's like, okay, I don't know if you guys have heard this metaphor before. For induction, it's like dominoes. You knock over the previous dominoes, which knocks over the next. And before, we were just hoping the singular previous domino would knock over the next one. This time, we're using n equals to k and n equals to k minus 1 to prove the next. All right, you got different types of induction. Sometimes you assume it's true for all of these to prove n equals to k plus 1. Right, but anyways, we can assume, right, we can assume this because it's like we've proven it. We started with the lowest number and then we keep increasing, so we can assume all of them. So this is an integer, this is an integer, this is an integer, and we're done. So hopefully that's a good recap, good enough recap for what induction is. And we'll switch back to the presentation. Okay, so remember the brackets n over r, that's like the number of ways to choose r things from n things, and it's equal to n factorial over r factorial times n minus r factorial, which is easy to prove. Okay, so this is our first identity for that thing. Right, if n is bigger than or equal to r, which is bigger than or equal to 0, and they're integers, then n choose r plus n choose r plus 1 is equal to n plus 1 choose r plus 1. All right, I'll give you guys a few minutes to prove that. Okay, so hopefully that should be quite easy to prove. I'll show the proof now. Right, the left, we wanted to prove n choose r plus n plus 1. No. N choose r plus 1 is equal to n plus 1 choose r plus 1. Okay, so we know what these are equal to. That's equal to n factorial over r factorial times n minus r factorial. This is n factorial over r plus 1 factorial times n minus r minus 1 factorial. And we want to prove that that's equal to n plus 1 factorial over r plus 1 factorial times n minus 1 factorial. Okay, so we got two fractions on the left, so we want to try add them together. And to do that, we make them have the same denominator. So we got r plus 1 times n factorial over r plus 1 times r factorial, which is equal times n minus r factorial. And that's just r plus 1 factorial, right? Times n minus r factorial plus n factorial times n minus r over r plus 1 factorial times n minus r factorial. And then this plus this is equal to n factorial times n minus r plus 1. And that's just equal to n plus 1, right? Because these two cancel out. And then that's just equal to n plus 1 factorial. Right? And we've proven it, right? Because this is equal to this. So, yep, that's that. So we know n choose r plus n choose r plus 1 is equal to n plus 1 choose r plus 1. Another way to prove it, right, in combinatorics with these like bracket things, I think these are called combination, the bracket things, I'm not sure. There tend to be many ways to prove these. So this was like an algebraic approach. We know this is equal to this, and then we did some algebraic manipulation to get the left-hand side into this, which is the right-hand side, and that's the proof. Another way to prove it, all right, we wanted to prove n choose r plus n choose r plus 1 is equal to n plus 1 choose r plus 1. So this time we'll focus on this side, right? The other time, in the last solution, we move from this to this. Okay, so consider n plus 1 objects. All right, this is our n plus 1 objects, and we want to select r plus 1 of them. Like, focus on this object, right? Select r plus 1 objects. We have a1, and we want to select r other objects from these, right? Because we already have one of the objects here. So if we select a1, then we want to select r more from these to get r plus 1 objects. There's n objects here, and we want to select r of them. Otherwise, if we don't select a1, then we got to select r plus 1 objects. Now we got to select r plus 1 from here. So this plus this is equal to number of ways to select r plus 1 objects from n plus 1 objects. This might be a bit confusing. Okay, but essentially what we've proven is n plus 1 choose r plus 1. That's equal to something. And that something is a number of ways to select r plus 1 objects from n plus 1 objects. And also the number of ways to select r plus 1 objects from n plus 1 objects is n choose 1 plus n choose r plus 1. So therefore these two are equal. And we have that. Okay. Next question. All right, we got Pascal's triangle, this time with like hexagons around it. The typical convention for Pascal's triangle is that first row of 1, 1. That's the 0th row. And then the first term of each row is actually the 0th term. All right, hopefully that's clear in the image. So we want to prove that n choose R, right, which I couldn't really write, so I did like a C brackets and R. Hopefully you guys can understand that. We want to prove that n choose R is equal to the rth term of the nth row. Again, you guys get a bit of time. Okay, the actual definition of Pascal's triangle that we're going to be using is each term is the sum of the two terms above it, and we get like the zeroth term of the zeroth row is 1, and then the zeroth and first term of the first row is 1 and 1, and then the other terms are defined as the sum of the two terms above it, and then prove that that implies the rth term is n choose r. If you guys aren't getting anywhere, then as a hint, obviously it's quite clear you guys should use the identity that I just proved, right? Because Pascal's triangle, well, at least the one we're using for this problem, it's defined as each term is the sum of the two terms above it. Yeah, and then also Pascal's triangle has infinite rows, so maybe use induction, because proving something for an infinite amount of things is a bit hard if you're going one by one. But induction kind of just does it all. Okay, hopefully that's enough time to do something. So what do we have? The definition of Pascal's triangle, I guess, is one. Oh yeah, just one. Okay, the first row, one. Okay, and then for every term below it, the term is the sum of the two terms above it. So this is one, this is one, this is one, and this is one plus one, which is two. One, one, three, three, one, one, four, six, four, one. Okay, and we want to prove that this is equal to 0, choose 0. Oh, okay, yeah, maybe I should have. Okay, that's my bad. 0, choose 0 is 1. Anything, choose 0 is 1. Probably should have said that. My bad. Okay, 1, choose 1 is equal to 1, choose 0. That's 1, choose 1. 2, choose 0. 2, choose 1. 2, choose 2. 3, choose 0. 3, choose 1. 3, choose 2. 3, choose 3. And then, for example, this term is this plus this, right? That's 4, choose 1, and 4, choose 2. So this would be 4 plus 1, 4, choose 1, plus 4, choose 2, which is equal to 5, choose 2. And that's correct, because 5, this should be 5, choose 0. Okay, which it is. We can just use that. Right, this is 6, choose 0. This is 7, choose 0. And then this should be 5, choose 1. Okay, right, because it's 1 plus 4, which is 5. And it's also choose 0 plus 4, choose 1, which is equal to 5, choose 1. 5, choose 2. 5, choose 3. 5, choose 4. 5, choose 5. All right, so based on what we've been doing so far, it seems very possible that we could induct on the rows, right? So this is the 0th row, first row, second row, third row, fourth row. And okay, so hopefully you guys understand how we're going to proceed with the proof. And just as a demonstration, I'll give kind of a formal, proper proof. Right? I type most of this, so I will, because my handwriting, as someone very rudely complained, is not great. I think it's pretty good, to be honest. Okay, but let the I and okay, let the IF turn and the JF row be A I J. If I was handwriting that, that would be A I J. Right, just like how you have A1, A2. This is A I J. We got two-dimensional thing here. Pretty cool. Okay, and we know that A O O is equal to 1, which is equal to 0, choose 0. And also, based on our investigation on the left, we know that A10 is equal to 1, which is equal to 1, choose 0, and 1 is equal to 1, which is equal to 1, choose 1. All right, and we can keep going, all right? The 0th row in the second, 0th term in the second row is equal to 1, which is equal to 2, choose 0. And so on. That's enough for our base case, right? If the first, this was already enough, the base case, right? Induction, we prove the base case, like the lowest n, and then we prove that implies the next few. Okay, so if it's true when n equals to k, okay, so for every term in the kth row, so I k is equal to I, wait, is equal to, sorry, that's my bad. J, I. Okay, so the first number is the row. All right, so we got the first row and the second row is equal to A, I. Then for any number, for I between these numbers, right? Because there are only those numbers in that row. They are like those are the only elements in that row. Then when n is equal to k plus 1, we got this is equal to this by the definition of Pascal's triangle, right? These two are the two terms above it. And that, by our inductive hypothesis, is equal to k choose I, k choose I minus 1 plus k choose I. And that's equal to k plus 1 choose I. And we're done. This actually isn't always true, right? Because if I is 0, the 0th term in that row, then we can't really do this, but we know that a choose k plus 1, 0 is equal to 1, which is equal to c of k plus 1 choose 0. Yeah, that's everything. If I is equal to k plus 1, then that does not work. Yeah, that doesn't work. Okay. K plus 1 is equal to 1, which is equal to k plus 1 choose k plus 1. And that's it. We're done. Okay, so since we're already past 9 p.m., if you guys want to leave, then fine. I actually have to go, but I do have some other people in this meeting who are willing to teach. So they can take over now. If they want to unmute.
I'll take over from now on. Go study for your stats exam.
Okay, bye guys.
I only got 3 people, it's a bit awkward. That's all good.
Don't worry, guys. We're going over something very important here.